So, how do we describe this? So we still have a fixed outcome, either flashes or doesn't flash, but there's no fixed number of trials. So basically, what do we do? A classic example actually is also clicks in the Geiger counter is similar as long as the radioactive material that you measure with the activity of that remains constant. That's also an application of the Poisson distribution. So the Poisson distribution, the one we'll be deriving now properly, there was also a request for more math, so I'll do a bit more math. The Poisson distribution that we will be deriving will apply to processes where, over the time we observe, the probability that some event happens will be constant. It can happen at any time. That's why the flash of lightning example is so, because usually over the course of a thunderstorm that varies, let's assume that it remains the same over the entire long period of the thunderstorm. That's where maybe a radioactive decay, where your decaying material decays so slowly that the activity remains essentially constant over the time period you're interested in. That might be a more appropriate example for a bunch of physicists. So, we start with the Poisson distribution, and then we modify it in such a way that it applies to our thingy. So, I know you can't see what I'm writing, but you will in a second. So I just copy this, and that thing is. Not too bad, not too good either, to be honest. Maybe a bit better. Okay, so you can read this. This is my rendition of the binomial distribution. This thing here, this is my timeline, so we said we don't have a fixed number of trials. I'm going to just divide up my timeline into little bits like this, into n little bits, and I'm just going to call every one of these a trial. Do we have a flash of lightning in one of these time bins, or do we not? That's my trial. Why does this not work? Why does this not work? Why is this approach not quite correct? Why does a binomial not apply to if I divide this up and then I have flash of lightning?
Just because fixed linear bypass, it's not fixed. There's the number of trials or the number of.
I can quite understand, but maybe.
We can take arbitrary number of points on the number line. So this is not. Okay, so in this case we don't have fixed number of trials.
Oh, we have a fixed number of trials. I just decided I'll take this time period.
Okay.
And I divide it into a fixed number, that's n. So it's 1, 2, 3, n. So these are my trials. I've managed to get a fixed number of trials. I say each time bin is one trial. There's a second aspect to the binomial that doesn't work. So I've got the fixed number.
Continue.
Somebody else? What was it? When does it apply? Fixed number of trials and?
Mutually exclusive events.
Two outcomes, right?
Two outcomes. Yes.
Success or failure, two outcomes.
Yes.
Here, I can have no flash of lightning, that's okay. I can have one flash of lightning. But I can also have two flashes of lightning. That's not two outcomes. That's actually infinitely many possible outcomes. I can have maybe I will have 5 flashes of lightning. Right? So, I have a fixed number of trials. Yes, there is a question back there.
What if you generalize your outcomes? Either a flash, we don't care how many number of flashes are coming, or no flash.
That would work. So that would work. So I could apply it to the case where I say either no flash or more than 1 or more flashes. That would work. Very good. Then I could apply the binomial distribution. It wouldn't, I think the answer is perfect, but it wouldn't quite get me to the Poisson distribution to which I want to get. Because for the Poisson distribution I want to count the number of flashes of lightning. If I don't distinguish between 1, 2, 3 flashes of lightning, I can't really count the total number of flashes of lightning. I lose that information. But it would apply. That would be a very nice way of using the binomial distribution for this. Perfect. So what I'll do something different. I will do this. I will make my time bins tiny. So I'll take tinier and tinier and tinier. I will take n going to infinity, and as my time bins get smaller and smaller and smaller, the probability to get a flash of lightning in one time bin will also become smaller and smaller and smaller, right? So I will have p going towards 0 at the same time, but we'll do it in such a way that n times p, which is the expected total number of flashes of lightning in my overall time period. So in my time period going, no, that's the wrong button. That's what I want. Going from here to here, that's my minimum time to maximum time. The total number of flashes of lightning, of course, has to be constant. The total number I expect. So that is constant. And we can call this constant something. Let's call this lambda. Okay? Lambda is the mean number of flashes of lightning we expect in my pattern. Now let's do it. Let's take this expression
Success of probability
and do this to it. Oh, come on. That was an unnecessary complication, I think. That's better. Okay, so let's do this. So we want to take the limit of this, where n goes to infinity, p goes to 0, and n times p at the same time remain constant. Taking this is a bit complicated, so I'll reduce the number of parameters. And I'll replace then p with lambda divided by n. And then I only need to take one limit, right? The one where n goes to infinity. So that's my first step. I want to take still this limit, but now it's this limit of lambda divided by n to the power of r. So that's this term. Now I do this term. 1 minus lambda divided by n to the power of n minus r. And then I have here n factorial, r factorial, n minus r factorial. Everybody happy? Good. I'll rearrange a little bit. So my first rearrangement, by the way, this is unrehearsed. I mean, I've done it in the past, but it's ages ago. So most likely, at some point I will make a mistake. And at that point, I need you to shout and interrupt us, because otherwise we waste a lot of time. So if you see me make a mistake, just don't hold back. But the first step I think is fine. I'll just put this one over here and this one over here. Then lambda to the power of r divided by r factorial, and then we have 1 minus lambda to the power of divided by n to the power of n times, I'll split this, don't really need it, but it makes it neater, minus r, okay. And then we have this, which is n factorial divided by n factorial times n minus r factorial. No, it's not n factorial, it's n to the power of r. There you go, the first one. And somebody shouted, so whoever that was, thank you. Good? Good. We can already do a few things with this. This doesn't depend on n, so I can take it outside. So we're done with that term. That's neat. This term, I will just give it to you without proof. It's a fairly well-known expression. This is e to the power of lambda. That's some of you might know it, some of you might not. I will not be able to prove that to you. I think it's not that trivial. But this is e to the power of lambda, this limit. And then we have this left, and I will show you that this is basically 1, this entire expression. So let's write down what we have. So we have lambda to the power of r times r factorial. That is this bit, and then we have e to the power of
lambda
minus lambda. Sorry, lambda but minus lambda, and that is let's do some. That is this, and then we continue with the limit. 1 minus lambda divided by n to the power of minus r, and then n factorial. I'll write this bit all in the numerator. So this is going to be n times n minus 1 times n minus 2 times many things times n minus r plus 1, and that is going to be divided by n to the power of r. All good? All good. And that is, we are nearly there, by the way. It might look messy, but we are nearly there. I'll write the bit in the top as, okay, so we'll have 1, 2, 3, 4 r terms like this that are multiplied together. So that means we'll have in the numerator n to the power of r plus something, some number, that turns out to be r times n to the power of r minus 1 plus
Professor?
how very annoying. Thank you for pointing this out. How long have we missed out on my beautiful writing? I don't know. Okay, so oh, come on. So, let's see. I think now we are okay. It's a bit. I think that's basically optimal. You can see everything?
Yes.
Yep.
Thanks for shouting. So, are you happy that we have the highest power we have is a certain instance of R, and then we have powers that are smaller, and we divide this by instance power of R, and actually we are. Oops. I'll just delete this. Etc. And therefore, these will all go to 0. This is 1. This term, this one here, that will go to 0. So this is all. This entire expression here is 1, 1, 1, 0, 0. Okay? I see agreement. That's good. That's important to me. So this is therefore lambda to the power of R factorial e to the minus lambda, and we have 1. This is the Poisson distribution. So, everybody happy?
Yep.
What you should, I think some of you followed this proof, some of you did not. That's fine. The important thing to remember is how we got there. I think that's what I find most important, and how we got there is by splitting up our time range into tiny bits. So we let the number of trials go to infinity, the probability of success in each trial go to 0 at the same time. This means that you can approximate binomial distributions with large n and small p with Poisson distributions, which is quite nice, because the binomial was quite a messy one, the expression. The Poisson, I can't think of any more beautiful expression that expresses the probabilities that something happens and how often something happens. And that governs a lot of particle physics, because a lot of what we do is we count stuff. And that applies a lot of times when you count things, when you count random things. So if we collide protons and protons in 40 million bunch crossings per second, that n is very, very large. Right? The probability that we get a Higgs out or something that's of interest is very, very small. So we use the Poisson distribution to describe the number of Higgses that we see in a series of data taking in the data set, or the number of anything we see basically. So this governs a lot, and it also tells us actually the fluctuation on the backgrounds we expect. So anything that is a counting experiment with where the probability at any given point in time, or inside my data set, that I get one is the same, that is governed by the Poisson distribution. The Poisson distribution has a certain has some key properties that we always look at. The expectation value, now that is lambda. That's how we constructed the entire thing. And the standard deviation without derivation, because at the end we are running out of time otherwise, that turns out to be the square root of lambda. That's another square root n, because lambda is something you count, then you call it n. That's another square root miracle. So the uncertainties are typically the square root of the number of events that you have. Technically, the uncertainty on if you find 10 events, the uncertainty on that is the number of events that you theoretically should get. But your best guess is then the number of events that you have. That's what you pick instead. So most of the time you don't know what you should get. All right. Everybody happy with this? This took a little bit longer again, but I thought there was need for some math in our thing. So that's the big result. This is the derivation we've just done. I promised you several times that I will upload the slides. I haven't done that yet. I will after this lecture, I promise. And that will then include also the derivation that we've just done. So if you didn't scribble it down in time. That's even the LaTeX code for it. There you go. So, that is my Poisson distribution summary. It's a beautifully simple expression that expresses the probability to find R events if on average you expect lambda. At one single parameter, that makes it so nice and simple. And that parameter is this expected number of events. And it also gives you the variance. So the standard deviation is the square root of this, which we have not proved. But I'm pretty sure you can prove it yourself with a bit of, it's infinite sums kind of thing. It's a bit of a nuisance, but it's not too hard. So I call it the square root of square root n, although I'll call it the parameter lambda because, but if I expect n events, then the uncertainty on this is the square root of the number of events. So if I expect 100 events, the uncertainty on this is what is n. All right. So this is the Poisson distribution. I've already told you that binomial becomes a Poisson for small n large, for small p large n. What the Poisson distribution, of course, also does, it becomes a Gaussian in the end if you have large enough lambda. So this is how the Poisson distribution looks for small lambdas. Here, lambdas we expect half an event, an average of half an event. Get used to fractional averages, right? We never expect to see one event. We either see 0 or half an event. We either see 0, 1, or 2. But on average, we can of course expect half an event. This is how it looks like. We expect one event, 2 events, etc. If you want to spot the parameter lambda for small values of lambda, take the ratio of the second of the first two zeros bin, because that's exactly that number. That's so here it's 1 and here it's 2. If it's larger values of lambda, just take the center of the distribution, that becomes a Gaussian. The Gaussian of width lambda of mean lambda and width square root of that one, because that's the standard deviation of the Poisson distribution. So that is the big 3 distributions. We've done them now with some thoroughness at the end. The binomial that we can sort of derive from first principles, more or less. And then we take the limit of infinite number of trials and the small probability of success, but a fixed average number of successes within our sort of time period or data taking period or whatever you have. Your data file is also fine. And then we get a Poisson distribution, and both of these become Gaussian in the limit of large numbers of events. And this Gaussian, well, this guy has only one parameter, the Gaussian has 2, but the Gaussian always inherits the parameters from whatever distribution you come from. So here, if it comes from a Poisson distribution, the Gaussian gets a sigma that is, it gets a mean that is lambda, and the sigma that is the square root of lambda. Right? Here, if the Gaussian comes from a binomial, it gets a mean of n times p, which is the expectation value for a binomial, and it gets a standard deviation that is this expression, which is n times p times 1 minus p. Which is very similar to this in the case of small p, but quite different in the case of larger p. So beware. All right. Any questions about this? Because then we have enough time to do the fitting, which I'm quite keen on. Quick question? Yes, please.
So, Professor, we considered different things for both distributions. For the Gaussian, for the binomial distribution, we had a set number of trials and mutually exclusive events. We had 2 either success or other failures. However, for the Poisson distribution, we sort of assumed something different. How come in such a situation where you assume different things for 2 different distributions, you got the same thing? Doesn't the interpretation of the Gaussian change for both those things?
No, it doesn't.
Yes, exactly. That's what I was thinking from the point you started. That at the end of the day, we get the same thing.
Yes.
What exactly has changed in both of these things, actually? That I cannot put my finger on that. Could you?
The only thing that changed from here to here is that it's a setup. Here I have a fixed number of trials with a fixed probability for a trial to succeed or fail, or whatever you call it, to get a 6 or not 6. Here, I don't have a fixed number of trials. Here I have a counting experiment where I have an expected number of events that I count on average, and I ask myself, how likely am I to get a few more, a few less, or exactly the exact right number. So I expect 10. How likely am I to get 0, 1, 2, 3, 4, 5, 4, 10, 20, 100? And that's what this answers. But the Gaussian tells you how likely am I, given that I have a mean of mu and a standard deviation of sigma, how likely am I to get between x and x plus 1 events? So the real problem actually that you should worry about is that these are probability distributions. This is a probability density function. The probability that I get exactly one value here is meaningless. So you will have to integrate a little bit actually in order to do this. So that is a one challenging bit that I sort of skimmed over because I want to do PDFs in a moment. But that's one challenging bit. You have to, PDFs only make sense when you integrate. And maybe because that's such a nice segue to the next part of the lecture, I'll just continue with that actually, if I may. I'll skip the homework, and we'll do, well, it's not quite. We'll do fitting. We'll do PDFs, possibly, if we fit very quickly, we'll do PDFs today. If we don't fit quite so quickly, we'll do PDFs on Thursday, which is tomorrow. Fitting will be something you do a lot, and I believe you've already done this in these computing exercises. We'll do it by hand. We'll have another look at it. I hope it will be not too repetitive. Usually I think it can be pedagogically very valuable to see things more than once, because it's very difficult to understand them the first time. So I'm quite happy that these things match. But yeah, so let's go ahead. So what I want is, I have some model. This model, that's a probability distribution we haven't, it's actually a probability density function. We will formalize later what this means, that we haven't really looked at. That's an exponential decay distribution. So I have lots of particles. In my case, this is often B mesons, and they're at time t0, and I look at which time they decay. And the reason this distribution falls off like this, or from your perspective like this, is that after a certain amount of time, I have fewer and fewer and fewer of these B mesons, so I find fewer and fewer that decay. But this is a distribution that you get out when your probability to expire is constant throughout time. So humans have a different distribution, fortunately, because our probability to expire is not constant throughout time. So the question I have, T is a measure parameter, tau, this thing I measure my data, tau is a parameter that describes the distribution. Given that I have a data set that tells me T, what is tau? What's the best guess for tau? That's what we are trying to do. And the first approach, we're going to do this with two approaches. The first approach will be a chi-square fit, the second an unbundled likelihood fit. Looking at the clock and looking at Vajit, I think we might not get to the unbundled likelihood fit. Well, we'll get there tomorrow. So this is type of thing used for bin data. So I make a histogram out of my measurements. I just put them into histogram bins. So all the times between 0 and 1 go in here, whatever I want to choose for my binning. And then I want to minimize some kind of distance between my function and the data. So the question now is, how do I define the distance, how different my function is from the data? I want a mathematical expression that says this, that quantifies how different my function is from the data, and then I want to minimize that. I can, for every individual histogram bin, I can measure the distance between the function and my data. And put here, I can put here. And then I can, I've learned now that adding up these distances, because they are signed and stupid, I add up the distance squared. That is not so different from measuring the distance between 2 points in space, because that is delta x squared plus delta y squared plus delta z squared. That's the distance squared. So we also add these things in quadrature. So we just generalize this kind of concept and add up the distances between what I see in my histogram bins and what my function predicts should be histogram bins. And I can do one better. And I do one better by saying, okay, but some of these have larger uncertainties, some of these bins have smaller uncertainties. I want the bins with smaller uncertainties to have a higher weight in my distance. So I divide every single one by the uncertainty. And I divide it by the uncertainty squared because I like to have a number that has no units and things like that. So it's, although it just counts. Anyway, I'll divide by the uncertainty squared. But this is actually, why this is neat, the square term in the uncertainty itself, why this is neat will become actually more obvious in a moment. But basically I want to match the square here. That gives it nice properties. So that's the chi-square. The chi-square is the distance, the sum of the distances normalized by the uncertainty squared. So if the uncertainty is very small, this will have a bigger contribution to the sum. If the uncertainty is very big, this will have a smaller contribution, not matter so much. And my plan is to minimize this. And we'll do that now. All right, are you ready? No.
Gentlemen.
This is not right, huh? Oh, come on. Sorry guys, I'm having trouble with my give me a second. There it is. So, this is my data set. We still want to, wait a second, actually, I think I might like to get this over here. No? It refuses to cooperate. Okay. Okay, you just have to imagine the life distribution. I'm a bit unhappy with this because I want you to be able to see what we fit while we fit it. So okay, that one's more cooperative. So that's what we want to fit. I'll put it maybe down here. Good. And this is my distribution. This is our data. The axis is in picoseconds. And I want you now to tell me what do you think is a sensible value for this tau parameter. So the tau parameter basically gives you a kind of typical or average lifetime of this distribution. Turns out actually it's exactly the average. By the way, you might wonder what this is about. We'll understand this, the importance of this better once we do likelihood fits. This is normalization that ensures that if I integrate the probability over all taus, this gives you 1. So the probability that something happens is 1, that's what you want. But the shape is determined by this part. So any guesses for a good value of tau? So if tau gives you a sort of typical lifetime of the thing, I need somebody to shout. Louder. Should I put in 5 minutes for now?
No.
2 days.
No.
50 microseconds. Come on, somebody say something.
So you should,
No idea how much time I have. All right, so let's see who wins.
Professor, you should find the area under the curve and probably that's all.
I just want to guess. You don't need to classify it. Just tell me a number that sort of makes broadly sense for the typical time lifetime of my beam meter. That's the average lifetime, basically. That's what Carl gives me. 2. Thank you. Brilliant. I am so grateful. So. Two is a completely, 2 picoseconds is a completely sensible guess given what we see there. And then we'll optimize it and see. So this is the fit that you get if you assume tau is 2. We get a chi-squared of 24, and chi-squared per bin, that's not so important for us right now, but chi-squared 4 is quite important. So I'll put this here. So this plot, that will give us the chi-squared, let me see what I think it might, let me do this, but okay. This is the chi-squared value, and this is the value for the parameter. Should we have a bigger or smaller parameter? To guess next. Do you think it's perhaps a bit bigger or a bit smaller?
Smaller.
A bit smaller. What would you put in?
1.5.
1.5. Let's put in 1.5. There you go. 1.5. And indeed, you can see this was our value for 2. 1.5 is better. So it also looks a bit better. But we were quite close. What should I do next? 3.
1.3.
All right.
No, not 3. 1.3.
3.
No.
What did I put in? I put in 3. 3 is here. So 3 is much worse. 30.
1.3.
1.3.
2.5 and 1.2. I'll put them both in.
1.
2.5
2.5 is 1.
and
1.3.
1.2. So 1.2. So it seems it's somewhere. So we want the minimum chi-squared, right?
Yeah.
So we're getting something here, I think. So any further guesses and values? 1.8. Good. I like that. 1.8. So it sort of makes sense that we are in this region. 1.8 was not too bad, I think.
1.6.
1.6.
1.6.
So 1.6, and then there was what the other one?
Yep, 1.6.
1.5.
1.5. Have we had 1.5?
6.5.
That's 5 we had. So maybe I just fill in a few in this area. I think we've sort of had it now.
Yeah. Some 1.6.
Just to make it sort of a smiley face. So I think this is it. So this seems to be the smallest value that we have. We could
1.6. 1.6.
1.6 seems to be quite good. We could fiddle around a little bit and see whether we get nearby something that is even smaller. So I could try, why not? I could try 1.65 and 1.55, but it seems very consistent that 1.6 is the, so if you drew a line through it, you'd also have it at 1.6. So let me see whether I can do this. This is usually a bit painful. Yeah, this is not what I wanted. Yes.
So, you want to drag it to the other side, maybe point it to 1.2 and then you will be able to drag it.
You want 1.2?
No. I'm saying that if you want to drag it to the other or zoom.
No, I don't want to drag it. I want to, it is possible to just select the lower bits somehow. If you just hover at the exact right place. But I don't know how to do it at the moment.
Yeah. So if you want to zoom out, put it on the 20 and drag it down. Then it will zoom out on 1.6.
So that's what I want to do. I seem to be unable to do this. So I can do this. can do this. Why don't we do this the way I want? Now finally, that's what I want. So just to focus in on the bit that's interesting, so near the minimum, and maybe I can win again actually. Yes, now I have, thanks Ajit, I have gained control over this, and I might even do the same thing here. Okay, so this is our sort of the zoom into our distribution. The minimum is 1.6 we said. So maybe we have
62 or
1.62.
1.65 is a bit better, right? So the minimum one is 1.65. So the interesting question now is, what is the uncertainty? And I will again not give you the derivation of it, but I think what you should find intuitively plausible is, the steeper this is, the higher the curvature here, the more pointy this thing is, the smaller the uncertainty. And if I had a very broad, in the limit I have just a flat line, I don't have anything. If I have a sort of broad line here, the uncertainty is a bit bigger. If I have a very steep curve, it's a bit smaller. And what I can do is the uncertainty is, I can get the uncertainty by moving from my minimum, let's call it 1.65. I move from my minimum outwards until the chi-squared has changed by a value of 1. Just take it as a rule for now. So here, 1.65, I think the curve would be around here, yeah? So that is 1.51, right? So let's write this down. I know you can't see it, but I will forget it if I don't. It's 5. Okay, well, we'll just, that would be, yeah, magic. This is not what you went to see, though. There it is. No. Too many things at once. No. I have got too many windows open here, but I don't want to go to Dropbox either. That's what I want. Right, so our estimate of tau is 1.65. Then we said if we go to about 1.51 or something like that, we change the chi-squared by 1. So we say plus, and then so that's 1.51, so 1.65 minus 1.51, that is 0.14. That's a bit more precise than we really need to be. So, and if we do the same thing in this direction, we should see a similar thing. So I would say we're about here, that's 1.76 or something like that. Yeah, 1.76, it's the same, more or less. Plus, minus 0.14. So I could, if I wanted to be very precise, I could have different, I could have an upper and a lower one. I could do, you can see it sometimes done like this, plus 0.13 minus 0.15, something like that, sometimes it's done. And that's done by Minui, typically that's the fitter you use, exactly in this way. It goes up and sees when does my chi-squared change by 1 in this direction, when does my chi-squared change by 1 in this direction. Most of the time, it's not worth quoting asymmetric errors unless they're really very, very asymmetric, because it's a pain in the neck in error propagation, etc. So if you can get away with symmetric errors, it's much better. So that's why, given the precision we have on our error estimate, I thought this is not worth it, so I'm just going to cancel it out. So that's our result. And I think that concludes my lecture. In time for coffee, I suspect, comes next, right? So thank you all very much for participating so nicely in our fit. There is there are two fitters actually now. There's Ajit's fitter that you have probably interacted with, I hope, and now you know what it does under the hood. It does exactly this, slightly cleverer. It uses some gradient descent, I believe. And then there's also amongst my Jupyter notebooks, where as I sent you to, there's also a chi-square just like that. So this is the by hand one where you search for the midpoint. So you can play with that as well. Thank you very much.
Questions?
Thank you so much, Professor, for the really nice interactive lecture. So can you please, like, in this we estimated a parameter, in fitting. So we can mention that parameters limit using confidence intervals, right? So when do we actually use prediction intervals when we are estimating some parameter?
I have no idea. What do you mean prediction intervals?
Like the confidence interval will tell you, let's say with some confidence level, that where the parameter, the true value of the parameter lies, right?
Yes.
And for prediction interval, it could tell you where the future predictions would lie with, let's say, 95% confidence interval, prediction interval. So where do we actually use that in particle physics or something?
I have to confess to you, I don't know what you mean with a prediction interval. Okay. If you mean the kind of things that my colleagues at Atlas and CMS use when they predict limits and this kind of stuff.
Yes.
These prediction intervals, they don't come from this, or hardly. They come from simulation. You might, of course, adjust your simulation based on the data you've taken previously, but you basically simulate your data set in such a way that it serves, you assume, for these limits typically you assume there is nothing. How, given the what we know about the backgrounds that we get, etc., where would the limit be if we continue to take data in the way that we assume we will? That's what this does, but that's simulation-based effectively. Sometimes you can do it analytically, but essentially it's simulation-based.
So normally we would mention a parameter with some confidence level, like 95%, 99, whatever confidence level we choose. We can mention that the true value of the parameter could lie within this range.
Yes, so I have given you this one, plus minus one, as plus minus thing. That is our 1 sigma confidence interval.
Yeah.
And that, in a frequentist way, says, I promise you, if you repeat this experiment an infinite number of times, then in 68% of the time, the true value will be within this confidence limit, and in 32% of the time, it will be outside. That's what this means in a very sort of strict sense. And you can do the same thing with twice as bigger, with bigger confidence intervals, like 95% or such, etc., etc. If things are Gaussian, it turns out if things are Gaussian, then this looks like a parabola, and this looks fairly parabolic to me. If things are Gaussian, and this looks like a parabola, then you can just double the size of my interval, and that takes you to a 2 sigma Gaussian interval, which is then 95.5%. But if things are not Gaussian, you have to be more careful, and then my rule to go where this changes by 1 changes to a rule, well, if I want the equivalent of a 2 sigma Gaussian confidence interval, even if this is not Gaussian, I just go to where this changes to 4, that's 2 sigma, 9, 3 sigma, so it's a square that you go for.
Yeah, okay, thank you.
And the magic is that this allows you actually to do non-Gaussian confidence limits, although it all refers back to Gaussians, interestingly.
Any other? Okay. Let's leave for the tea then, and after tea we have 2 more lectures from the other colleagues. Let's thank Jonas Rademacker once again.